Quiet. So we were discussing carry look ahead adder, right? Carry look ahead adder. So once again, the equations related to that. So if you see, carry is equal to C out is equal to AB plus A XOR B multiplied by C in. Okay, or multiplied or ANDed with C in. So this becomes my generate term and this becomes my propagate term. So I rewrite it as C is equal to C0. Initial one will be C is equal to P plus G C in. Okay, this we have already written. I'm just writing a quick recap. What? Sorry, G plus P. Generate plus. So G plus P C in. So I can write as G0 plus P0 C minus 1, the one which comes in from the previous stage. That is the C in. C1 becomes G1 plus P1 C0. I substituted with the C0 from the previous equation. So I got it as, I'm just writing the final one. C2 becomes G2 plus P2 C1, which is equal to G2 plus G1 P2 plus P2 P1 G0 plus P2 P1 P0 C minus 1. Okay. Similarly, C3 also you can write. Now, let's draw the circuit for this. So I need additional hardware, as I said earlier. So what, in order to have this, so I can generate all my GI, okay, GI using AND gate. Using an AND gate, I can generate all my GI. Using an XOR gate, I can generate all the PI. Okay, this I can generate initially. So G and P is generated. Okay, once that is generated, now I have my carry look ahead adder logic would be something like this is carry look ahead adder, or carry look ahead adder logic, or I can call it carry generate. I'm going to generate my carry, each of my carry. Okay, so I call it carry generate. So in carry generate, what do I need? I need all these G3, P3, G2, P2, G1, P1, G0, P0. Now, can I get all these? This is, I can get this using this AND gate and XOR gate function, right? So whichever I want, whether I want G0, P0, G1, P1, all this I can generate because I know the numbers that I want to add, because A and B are known. So this can be generated. So this I can give as input. Now, what is the next stage? Suppose if I want to calculate C0, it should be, I have if this is an adder circuit, I have the C minus 1 coming in. Okay, not adder circuit. This has one more input, which is the C minus 1. Okay, this is also an input to the circuit. So if that is there, I do P0 into this. plus G0. This gives me what? C0. Okay. Next equation is P1 G0 I have to do. So I take G0 from here. I do. And then I have P1 P0 C minus 1. So the C minus 1 I take. I also have P1 and P0. And then this G1, all these three, this two and output and this all together I have to OR it. So I will get C1. Yes or no? Okay. So this way for each of them I can write and I will get C2 and C3. So if you see how many levels of delay have I introduced in this, I mean after, so once I get, okay, wait, we'll leave it there. So now to compute the carry, how many stages of delay is what I'm asking. I have only computed the carry, I have not computed the sum, right? I have, in advance, I'm trying to compute what is this C1, C2, C3 on the basis of C minus 1, my initial carry in. Okay, I have tried, this part of the logic is trying to generate the carry alone. Now, when I generate the carry, how many stages of delay do I have is what I'm asking. This is going to be additional. Now, from the full adder circuit, I'm adding this logic additionally, right? So now here that means to generate G3 to P0, this initial, this section, if I have to generate this, I have AND gate and XOR gate there. Okay, so one stage of delay for that. So this will have one stage delay. That is the initial part, that I have AND gates and XOR gates appropriately to generate my G3 to P0. Then now I come inside the carry generate block. What do I have? If you look at each of these terms from C0 to C2, which I have written here, you can see that I have some AND operations, right? I'm ANDing some terms, what P1 G0 maybe, or P2 P1 G0, depending on this. So I have AND operations, and finally all those AND operations output, I am ORing them, okay, to get my C2 or C1 or whatever. So that means I have one stage of AND gates, and then I have another stage of OR gates, right? All these AND operations can be performed simultaneously, okay, at the same level. Do you get it? So then, so I have two stages here. That means here I am adding two stages of delay. So totally to generate my carry, I have three stages of delay. Okay, this is to generate my carry alone. So how many ever bits of carry I have, I can generate it simply by generating the G0 to G0 up to G, whatever, Gn, let's call it, and P0 up to Pn, which is just doing the AND operation and XOR operation of those two inputs. I will be able to generate all these, how many ever I want to generate. So that has only one stage of delay. It is either a single gate to do that. Okay. What is the doubt? Okay. And then inside the carry generate portion, I have many AND gates finally, which are all together. So all the AND gates can be executed simultaneously. So that is one stage of delay, plus the OR, which comes after that. So two stages within that block. Okay, two stages of delay within that block. And then finally you get all your carry. Okay. Now once this carry is generated, now I have to compute the sum. So what will be the sum? I have sum means I have S0, S1, S2, S3. Once I have the carries, then I can compute the sum easily. Okay. I don't have to wait for the carry to propagate from the addition of the first bit to the second bit. No. Initially, we are generating it. Okay. So now, what is S0 basically? S0. S0, if you see the least significant bit. So I have A3, A2, A1, A0, B3, B2, B1, and B0. My S0 is going to be this, right? Addition of A0 and B0 will give me this thing, right? So according to sum, what is the expression for sum? A XOR B, right? That means if I do A0 XOR B0, I will get the sum S0. Yes or no? Yes. So now this, do I have to do it separately? I have already used it to generate Pi. So that means my P0. Okay, what would be my P0? P0 would be A0, B0. I XOR it, I get P0. So this P0 is the same as my sum S0. Do you follow? Is that clear? Why we are getting P0 as, P0 and S0 as same? Okay, because it is the same XOR operation that I need to use to generate the sum. Okay, so in the initial, that is here, since there is no carry involved, I don't have a problem. But from the next stage, I cannot say it that way. So I'll just redraw this thing. Okay, so here I'm not drawing what comes within the CLA logic. So CLA logic. I have all my inputs D3, D3. So here I have D0. Okay. Now what will be the next sum? Next sum will be, see, next sum, if I go back to the previous page, you see, next sum is going to be, I will have some carry coming in, no? C0. Yes or no? I can have a carry which is either 0 or 1, but there is a carry coming into the next bit. So what happens? Now I have to do this and this, right? So A1 and B1 means it is A1 plus B1 is same as A1 XOR P1, B1, which is equal to P1. So P1, and then I need to XOR it with C0 if I have to get the sum for that particular bit position. Yes or no? So here what I do is I take P1. P1 is already generated in this stage. There's nothing additionally to do. That and the carry from the previous stage. If I XOR, I will get some bit 1. Next, the carry from the next stage and P2 will give me S2. S3. And this is my final carry C3. Yes. Hmm. Yeah. Delay of each, see, you all gates do not have the same delay. This is just for understanding the concept of delay, that I have said that XOR has more delay than AND gate or OR gate. Okay, so but we are just trying to understand what is propagation delay. So here we are not bothered. So in many of the applications, when we study for theoretical purpose, we assume that all the gates have a nominal delay which is equal, like unit delay. I say one unit of delay for each gate. Okay, so that is the way we are proceeding here. It is not that what I mentioned, that delta, everything has a delta delay. No, everything has different delay. So we are only trying to understand the concept of propagation delay. This delay and all those things for every gate, that is given in the manufacturer data sheet. So that varies from IC to IC depending on the technology used. All that it varies. Okay. Basic gate. See, now how do I construct the gate? I have different technologies I can use. I can use MOSFETs. So then in that case, CMOS technology. Am I using CMOS technology? We have not mentioned about technology and all. So then there is ECL logic, TTL logic. So different ICs are based on different logics. So in the manufacturing sheet itself, the data would be provided as to what is the propagation delay. So now you don't have to, there are mechanisms to calculate the delay. For that, you have to go to transistor level representation. Okay, this I'm just drawing. I have mentioned this once before, that if I If I draw, this is my NAND gate. I draw my NAND gate like this. But if I am going to represent it at the transistor level, it's going to be like transistor is the basic building block with which we make gates. Okay, so that is one level lower. We are not going to that level of abstraction. If I have this as A and B, this is A, this is B, and I apply, this is the power supply, this is the ground, and this is the output. Okay, if I want to get AND from this, I need to invert it, right? And after the NAND, I need to put one more gate if I want to get A and B. In that case, I have to give an inverter. So this circuit is, so for this, we have some characteristics specifying the transistor, like width and length of the transistor and all. So that is all, that will get more complicated and we don't have time to go into all that. Okay, so depending on that, only this propagation delay values and all are computed. Okay, it is not that. Yes, Lara. So that's why I said it is technology dependent. This is CMOS technology that I have drawn here. Okay. So you don't have to learn this. I just said because you asked. Okay, this is not for you to cover. So there we were here. So now, yeah. So is it clear how we got the sum from this carry look ahead process and we generated the sum? So now sum, again, we come back to delay. I said up to here to generate the carry, we have three stages of delay. That means now if I have to generate the sum, how many stages? 4. Okay, one more stage is added. Okay, so now for sum generation, I have 4 stages of delay. Okay, now this 4 stages of delay will be constant if I'm going to make a large circuit like an 8-bit carry look ahead adder. Okay, all my inputs are going to all my carry, I can generate all my carry just using this C minus 1. Is it not? Like if you look at the previous uh, here, according to the equation, in all the cases we have eliminated the dependence on intermediate carries. Everything is depending only on C minus 1, right? So using that, I will be able to generate as many carry as I want. So that means that I can also generate as many sum bits as I want, right? 8 sum bits also, it will go this way. If I'm able to generate from G7 to G0, then I can generate, and P7 to P0, I can generate sum bits from S0 to S7. Okay, so the delay involved will be the same. So I have only 4 stages of delay. But if you remember what we mentioned about full adder circuit, the carry has to go this way. Carry will go from, this is my full adder 0, then the C0 has to come here, only then this addition can take place. And C1 has to come here. So then or which is called C3. Okay, this is C2. So initially my first carry, my first sum, I can generate it immediately because it is dependent only on this, on C minus 1. Okay, so here there is no delay. But the moment I come here, I need, this carry has to come. So there is a delay of, okay, there is a delay involved, which will be the delay of the gate. So if this has one stage delay delta, here to get the sum, it has to come here and get. So I will have 2 stages of delay to get this. Okay. So similarly, I will have 4 stages of delay to get the carry out. Yes or no? As many stages, that much of delay I have. But if I have 16-bit adder, means I will have 16 stages of delay. But according to CLA, if I'm using, it is only dependent on C minus 1 and I can construct a CLA of 8-bit width also, okay, a carry or a adder of 8-bit width, I will still have only 4 stages of delay. That is 4 delta would be my delay. So this stays kind of constant for if I'm trying to build a block, okay, all together. Okay, so that variation is there. Okay, that we are able to bring down the delay significantly by adding extra hardware. This is my extra hardware, the CLA logic. What I have there is the extra hardware that I'm adding. And based on that, I'm able to significantly reduce the delay in the circuit. Okay. Now if you see here, now if I see C0 has how many terms? There are two terms. C0 is equal to G0 plus P0, C minus 1. Now C2 has three terms. I mean, C1 has three terms, C2 has four terms. So if I have C8, how many terms will be there? 9 terms will be there, right? 9 terms. So one more. Is it not? 10 terms, sorry, 10 terms. Okay, C8. Okay, so now that means if I have 10 terms means one term will be the last term will have, I have to OR all the terms together, right? So that OR gate will have as many inputs as the number of min terms I have in this expression. So that, can I go on having how many ever inputs as I want for a gate? I cannot have it that way because it will deteriorate the performance of my gate. So there is a maximum level of inputs or maximum number of inputs that can be provided to a gate. And that is also something that manufacturer mentions in the data sheet. Okay. So I can have a maximum of 3 inputs to a gate or a maximum of 4 inputs to the gate. So why I cannot go beyond this? Wait, why I can't go, I will say. So that maximum number of inputs that can be applied to a gate, we have a term for that. It is called fan-in. This is a fan-in of a particular logic gate. Okay. So that means if I have a gate like this, and so the fan-in will be 3, the number of inputs that I can give. Okay. So there is a maximum number that I can give. And if so another gate could have 4 inputs. So in this case, the fan-in would be 4. Why we say that we have a limit on the number of inputs that a gate can drive? That is because of the factor that what do I mean by a gate? A gate gives an output 1 or 0 depending on the inputs. What is it doing? It is switching, right? Depending on the input value, it is giving us an output. Now a gate, if we always give a supply voltage, it is like it is not going to give us 0 and 1 directly. What we consider is that the output is a voltage. So I say that, okay, if the output is between 0, it will always not be 0, and 1 is representing 5 volts, suppose. Okay, 0 is represented by 0 volt and 1 is represented by 5 volts. It is not necessary that your gate will give you an output which is exactly 0. So it might be 0.2. Okay, or something. So up to a permissible level, there's a level up to which I can read it as a 0. Okay. And there is also a level, maybe it will be 4.8 here. It's not giving me 5, it will give me 4.8. So anything between 4.8 volts and 5 volts, I say it is level 1. And anything between 0 to 0.2 volts, I say it is level 0. But what happens is that when I try to increase the number of inputs, my gate will not be able to generate a strong 0 or a strong 1. So this value might fluctuate. Maybe it will go to 0.5. Okay. Or this voltage level might dip to 4.2. Okay. So I'm not able to generate a strong 0 or a strong 1 if I continuously add on inputs to a gate. That is why manufacturers specify about how many number of inputs you can have, maximum number of inputs that you can apply to a gate. Okay. So now when you will do hardware experiments, you will see that we are using 2 input AND gates or 3 input AND gates. There are different kinds of things like that. Okay. So there are different ICs for that basically. So this is the reason. That means it will degrade the performance of the gate if I increase the number of inputs beyond a certain limit. So that limit which we set is called fan-in. Same way, now I have one more thing called fan-out. Okay. Now I have an output of a gate. This output can be driving multiple gates, right? It can go as input to multiple gates. You have already drawn circuits, so you are aware that we can do things like this. Might be going to a NOT gate, this might be going to another NAND gate, and so on. Okay. So now how many gates can this output drive? Okay. Can I give it to any number of gates? Tap the signal and give it to any number of gates. What happens now if I'm talking about So it is possible that again it will not, it will degrade the performance in this case also. Okay, so it will not switch as desired from one level to the next level. So because of that, there is also a limit or a cap put on how many output or how many gates that the output of a particular gate can drive, and that value is called fan out. Okay, so the number of gates that the output of a particular gate can drive is called fan out. Okay. One was fan in, how many inputs can I apply to a gate? Similarly, fan out is taking the outputs, which all gates can I, how many gates can I apply it as an input to directly? Okay, so there's a limit on both these values so that the performance is not degraded. All right, is that clear? Okay, so these three terms are very important when you talk about performance. Which are the three terms? One, we spoke about propagation delay. Propagation delay is the most important parameter. When you design anything, any kind of circuit that you design, I want to keep my delay less. So that when I say delay is less means my circuit works faster. So I want fast operation. So it is necessary that I keep my delay to a minimum. So always the design, what we try to design is always with this interest, to keep my delay to a minimum and also optimize the space. So have lesser number of gates. So when I have lesser number of gates, I have lesser space occupied, so lesser cost involved in manufacturing and so on. So these are some of the parameters that we depend on. So okay, now let's move on to this. So CLA, I hope CLA is clear. Carry look ahead adder, how to generate and propagate all those terms. If you know, I can eliminate the need for intermediate carries. So that's how. Now, now we have something called BCD adder. Okay. Now I have an adder circuit. You know, adder means whatever. Suppose if you have a calculator, you give inputs. You give inputs. Suppose if I want to add 7 and 2, okay, it gives me 9. Okay, it's displayed as 9. But what happens inside the calculator? It is again binary. So what you enter is converted, is taken in as binary, converted to binary, and then you do all the operation, and then it is converted back into BCD and displayed. Suppose if I have 7 plus 5, I should get the output 12, right? I want to see it as 12 and not the binary representation for this particular one. So BCD adder is important in that way. If we see that is a particular application where we will use a BCD adder. So now let's see what happens now in BCD adder, the same case, okay? Binary, if I'm adding this in binary, 7 is 0, 1, 1, 1. And 2 is 0, 0, 1, 0. So my output is it not? Now, what happens when I add 7 and 5? 7 is 0, 1, 1, 1. 5 is 1, 0, 1. So, 0, 0. No, so not 0. 1, 1, and 1. Okay, 1, 1, 0, 0 I get. Okay. But now, if this is okay, if it's a binary adder, I don't have a problem. If this is a binary adder, it is correct. This is the representation for 12 in binary. But I don't want this. No, this is not BCD. BCD has only digits from 0 to 9. That means these conditions are not, don't care. If you remember in BCD, anything beyond 1001 is don't care. So I cannot represent it as 12. If I'm, in BCD representation, I cannot convert it. So now I have to look for a mechanism by which I can change the numbers, which is a BCD sum, sorry, a binary sum to a BCD sum. Okay, I have to do something to do that. Okay, so now if I see a binary adder, it has two numbers. Okay, I have number A and B. It could be 4-bit. Okay, it's 4 bits each. So so minimum value could be 0, right? Both the numbers can be 0. So my sum is going to be 0. And here, or it could be maximum, it could be, what does the BCD means? Maximum is 9, right? This is also 9. So maximum value that it can go up to, my sum can go up to would be 9 plus 9, 18, right? So beyond that, so that is what I have to represent in this. Okay. So now let's draw the truth table. Before drawing the truth table, 1 minute. Here, see, now if I want this, okay, what is the meaning of this? If I'm saying BCD, the same thing. 7 plus 2, I added, I got this as the answer. This was 7 and this is 2. When I added, I got this as 9. Okay. 9 means, so this is 1001 is 9. And I don't, my MSB could be 0. I can have an MSB because up to 18 it goes. So I can say that MSB is 0. So I just write it as 0. Now when I'm adding 7 and 5, I should get it as 1 2. I'm getting it as 1100. This is my 12, that is, but this is not BCD 12. This is not BCD 12. Okay. BCD 12 should come 1 2. That means I should have an MSB. This is MSB I'm writing here. So I should have an MSB which is 1, and this should become what? 2 means it has to be 0010, right? Then this I can call 2 and this is 1. I have to convert this into this form. This is my BCD sum, I mean binary sum 1100. How can I make it as 1 followed by 0010 is my question. So how will I do that? How can I make it plus 6? Okay, plus 6, because if I add 6 to this, what happens? 1100 plus 6 is 110. If I add 0, 1, 0, 0, and 1 is generated. Do I get it or not? So for any number which is generated which exceeds 9, I am supposed to add plus 6. Now first number, I get 9 as sum, it's fine. 9 up to 9 is okay for me. So if I add 4 plus 5, I get 9. If I add 6 plus 3, I get 9. All this is okay because I can represent it. The moment I add 8 plus 2 becomes 10. I have to get 10. I have to get 10. But how do I get 10? Because in binary, 8 plus 2 is 1, 0, 1, 0. Okay, this is 10 in binary. Now this, if I add 6 to it, when I add 6, 1, 1, 0, it becomes 0. So that means I have to make my least significant nibble. Nibble means group of 4 bits. That least significant nibble, I have to make it 0. And then the next one has to be incremented to 1. So if I add 6, this becomes 0. So this is 1 and this is 0. So now 10 is generated. That is why for every number beyond 9, if the sum generated is more than 9, I am supposed to do this correction. Okay, correction, so that I get 1 0 1 1 1 2 up to 1 8. Because only up to 1 8 I'm generating. 9 plus 9 is the maximum I can add if I'm using two BCD numbers. Maximum I can generate is that much. So is it clear why we add 6 plus 6? Yes or no? Okay. So let's complete the truth table now. See, now when I'm generating up to 18, I'm writing the sum up to 18. So up to here, this for 1111 becomes 15. Okay, 1111 is equivalent to 15. So beyond this, I, if I add one, I get 10000. So I'm totally representing it using 6 bits now. Okay. So if I need 6 bits, so initially also I add that 6 bit before, not 6 bits, 5 bits, 5 bits. Okay. Okay. Now, similarly, we will write with 5 bits, we are going to write the BCD sum also. Okay. BCD sum up to 9, you can write. Okay. 17 and 18, I will write here, the BCD sum. Okay, up to 7, we have written it as it is. Up to 7, you can see the sum is the same. And beyond that, not 7, I mean, up to 8, 9, it is the same. After that, it becomes 10, right? 1, 0, 1, 1, 1, 2. That way it goes. Okay. So last one, here it is 1, 8. So now I don't have an adder which can do something like this. Now I have a full adder circuit. That is my standard circuit. Now how do I, convert my full adder to perform BCD addition is the question. Okay. So we have the standard full adder circuit and we are supposed to uh, change it accordingly so that we are able to perform BCD addition. Okay. Now how that means, if I have a full adder, when I generate the sum bits. Okay, sum is generated, carry is generated. Now, so I have to figure out how do I convert this problem using a full adder. How do I implement it? Okay, so let's look at that part. So now this bit, I call it as this additional MSB that I have. Okay, I call it as C star. Okay. Now, if you see for numbers, where is C star equal to 1? C star is equal to 1 in the last three cases, 16, 17, and 18. You can see 16, 17, 18. Okay. C star, this is equal to 1. Okay. So that means that if C star is equal to 1, in all those cases, I need to do this correction, right? I need to add that 6 because 16, 17, 18 are numbers I have to add for more numbers. After 9, from here I have to add 10 onwards. I'm supposed to add. But distinctly by looking at the truth table, I can say that for 16, 17, and 18, the C star is 1. So the moment C star is 1, I can understand that I have to do the correction. I have to add a 6. Okay. So that is one condition. When C star is equal to 1, I have to add 6. Okay. So what we are doing is initially we will add like normal adder, full adder circuit, 4-bit full adder. Okay, 4-bit full adder. I give inputs from, I have my inputs B3 to B0, and I have A3 to A0. I add them. I get some sum bits. 4 sum bits I get. Okay. So I call it S0. This is S3. Okay. Now I have to decide depending on the C star value, whether I have to uh, add a 6 or not. Okay. If C star is 1, I have to add the 6. That is understood. Now, one more case. What about the other cases? If you see, if I can see that if I have in all these cases from 10, I'm looking at cases from 10 because from 10 only I have to make the correction. So, what is common in that? If either this value, see, I can see in all these cases, S3 is 1. If okay. This is a sum, so it is S3, S2, S1, S0. Okay. This is a sum. I have generated the sum. It is not A3, A2 and all because already addition has been done is my understanding. Okay, I'm just showing how to convert binary sum to BCD sum. So S3, S2, S1. If you see S3 over here from the number 10 to 15, all the cases it is 1. Okay, and so I do a correction when S3 is 1, and in these two cases I have S1 is 1. Okay, S3 and S1 is 1, or when S3 and S2 is 1. Both of them are 1. Okay. So either when C star is 1, I have to do a correction, or what are the other cases? I have to see which combination. See, this combination does not work for many cases. Up to this position, you know that S3 is not 1. Okay. That is up to the number 7. My S3 is not 1. So this condition will not work there. So that is correct. I don't need to do correction there. Now, in this case, if you see in 8 and 9, this S2 and S1 are all 0 in both these cases, in 8 and 9. So there also it will be false for this condition. So it does not apply to anything above 10. Okay, so this condition will perfectly work for all the numbers generated from 10 onwards. Okay, so 10 to 15, this is the condition that I have to look for. And if it is 16 above, just C star will be able to give me the output. Okay, so that is the correction part. Okay, so I will show you how it looks in the circuit. Is that clear how we have written this thing? Okay. So now now, what is actually C star? C star is the carry, right? 4 bits are being added. C star is the 5th bit generated, means it is like the C out. C star is equivalent to C out. Okay. So when I add these numbers, I get C out. So now the condition was, if like in the previous page I said, so it is either C star or S3, S1 or S3, S2. Okay. If this condition is satisfied, then I have to add 6. Okay. This is the condition. So now I'm going to tap the signals accordingly and draw the logic for this. Okay. So I have a big OR gate because there is an OR operation being done. Now I need one more adder. Okay. Why I need? I have to add 6. Right. In some cases, I have to add 6. So that whether I need to add 6 or not is dependent on this condition. Okay. So now if any of this is true, that is, if C star is true, if C star is 1 means, if any of this is true, this output is going to be 1, right, of this gate. If S3 and S1 are 1, also the output will be 1. Or if S3 and S2 are 1, then also the output will be 1. So any one of these conditions is satisfied, the output is 1. Now this output is 1. What I'm going to do, this is that output, okay. So let me call it C. Okay. And these sum bits which are generated, I have to feed it to the next adder, because whatever was my original sum, I need to do correction or not do correction. So I need another adder. Again, I have a 4-bit adder here. So I give these signals like this. So that is S0, S1, S2, S3. Now this becomes one of my bits, like B3 to B0. This becomes one set of bits I'm adding. What do I add it with? I have to add it with 6. So I'm giving my next set of adding bits over here. Okay. So I have, this is B0. Then B1, B2, and B3. Okay. Now B1 and B0. Now one case is case 1, no correction. In that case, I do S3, S2, S1, S0 plus 0, 0, 0, 0. It stays the same. Yes? So I get S3, S2, S1, S0. The next case, case 2, I have to add 6. So that becomes S3, S2, S1, S0, and I add 0, 1, 1, 0. So this is going to be, this should be my B3 in those cases, wherever I have to. So B3 and B0. Okay, this is B3, this is B0. They are always 0, right? So I can label them as 0. I can give 0 input to both. Okay, in all the cases, they are 0. This is B3, this is B0. In case 1 or case 2, the bits B3 and B0, if you see, when I'm adding 0 also, B3 and B0 will be 0. Correspondingly, when I add 6 also, it's the same. Now I have to change for S2 and S1, right? So what I do, this one, what is coming out, it will be a 1 if I need to do correction. That I can give it combined to these two, okay, as input. So that means if the C is 1, it will be 0, 1, 1, 0. Okay. And when is C generated as output? It is generated only if those conditions are met. When C star is 1 or S3, S2 is true or S3, S1 is true. Okay. Only in one of these cases, we will be able to generate this one. This is C. C is equal to this, I'm saying. Okay. So this C is generated only if any of these conditions are true. Otherwise, it's going to be 0. If it is 0, I am not making any correction. That means if it is 0 means all will be 0. If this C is 1 means it will be 0, 1, 1, 0. So accordingly, depending on that condition being satisfied, either a correction is made or the number is outputted as it is. Okay. So this is how I convert a binary adder to a BCD adder. Is it clear? Okay. Okay, so now we are done with adder circuits. Now let's move on to subtractors. Any doubt in this? If you have any doubt about the construction of the circuit, you should ask. Okay, so it is, the challenge is only about how to derive this logic. right? From the adder, how do I know that I have to add 6? If you observe, you understand that you have to add 6 to make it a BCD sum. But how do I do it? So 6 means, how do I generate that 1 1 as the next thing? Okay. So now the sum, this will give me my actual sum. So I have two stages of addition here. Okay. With the carry of the first one being modified to give the second input. So this carry has been modified. C star has been combined with other things to give me the input of it. So now let's look at subtract. Yes. Yes. Hmm? 5 bit, yes. This is a carry also. This will come as C. Okay. That is a C. Okay, final C. C out. This will be a C out also. Now half subtractor. Okay. So if you have an ALU, that is arithmetic logic unit, you not only perform addition, you also perform other operations like multiplication, subtraction, and so on. So let's look what a half adder circuit looks like. So a half adder. This is Boro, sorry, Boro and difference. Okay, Boro and difference. So don't write it as A and B, write it as X and Y because we have Boro and difference. X and Y. Okay. So when I'm subtracting 0 and 0, my I don't need to take any Boro. So the difference is 0 and my Boro is 0. Okay. Now when I take 0 minus 1, what happens? 0, I cannot directly subtract 0 minus 1. So I have to borrow some 1 from somewhere. So that borrow is 1. And if this becomes, then it becomes 2. So 2 minus 1 is 1. Okay, so difference is 1. Okay. Next one, 1 minus 0 if I do, just 1. I don't have to take any borrow. Difference is 1. Now 1 minus 1. 1 minus 1, 0. Right. Okay. So if I'm going to write the equation for my difference, difference is going to be x bar y plus xy bar. It is equal to XOR. Okay. Same like sum or difference is generated. What about borrow? Borrow is generated only in this condition, right? This is the only case I have a borrow is x bar y. Okay. So if I'm going to draw the circuit of the same, I have okay. So borrow is equal to x bar y. Have I not taken? Yeah, x bar. I have taken it from x bar. This point is x bar. So x bar y. And this is the point I have taken y from. And then the other one is x bar y plus yx bar. I know. Xy bar. Okay. So that you add, give it to an OR gate and you get difference. Okay. Now full subtractor. Is it okay? The truth table. So first case is 0, 0, 0. There is nothing to do. If you subtract, you will get 0. You're not borrowing anything also. Now 0, 0, 1. So x minus y, if I'm doing 0 minus 0 is 0. Then I have to do 0 minus 1. 0 minus 1 means I have to borrow something from the somewhere. So that means this becomes 10 now. 10 or 1 0. So it becomes 1. So I have a borrow coming in. So that's why I have a borrow also and a difference of 1. Okay. Next one, 0, 1, 0. 0 minus 1, I have to take a borrow if I have to subtract. So I have a borrow. Then this becomes 2. So 2 minus 1 is 1. And 1 minus 1 minus 0 is 1. So same way you can write for all the cases. If you look at the last case, 1 minus 1, 0. 0 minus 1 I can't do. I need a borrow. So I took it. And then it becomes 1, 0. So 1, 0 minus 1 is 1. So I have a difference of 1 and a borrow of 1. Okay. Yes. X minus y minus z. Okay. Like addition we were doing, the addition of each of the bits, same way. So if I do 1 minus 1 minus 1, I have to do 1 minus 1 gives me 0. I'm doing the last case. Okay. 1 minus 1 gives me 0 minus 1. 0 minus 1 I can't do unless I take a borrow. So I take a borrow. So borrow becomes 1. This becomes 1 0 now. 1 0 minus 1 is 1. Okay. So same way each case you can write. Now the circuit for this. Okay, so let's write for the borrow. Okay, borrow. If I'm going to draw the truth table for borrow, zero, zero, one. Okay, and let me group it. One group is this, so I write that I'm writing for borrow. Okay, so B is equal to. In this case, the row is the same. That's x bar and z. So I form the second group. Again, row is the same, which is x bar y plus this last group. It will be yz. Okay. So this is the term for. Okay. Okay. So here, since it is all represented using and or operations, this is borrow is represented using and or operations. I can even write these expressions. Difference can be written as difference. The first case is here where I have the value 1, that is x bar y bar z plus x bar y z bar plus x y bar z bar plus x y z. Okay. This also is in the form of or and I can come. You can eliminate it in this one. Why? How? That theorem asks you, so which is in the complemented form, which I have in both places, I have x bar. I cannot use consensus. I should have, if it was x bar y plus xy, x bar z plus xy, then I could have used. Okay. Here I have one of my variables should be in both complemented and uncomplemented forms. Only then consensus theorem can be applied. Okay. Here I cannot eliminate anything. Okay. So this way, now both will be, I can draw it in the standard form using and or gates. Both these equations. Yes. Yes, yes, you can write. I was just going to say that. So this I just mentioned so that you can write both the borrow and the difference using the same standard gates, standard logic gates. That is only uh, basic gates. I mean, and or and complement not. You will be able to write. You can also, that is for you to do. Reduce it to what XOR or XNOR or whatever you get. Okay, so you can convert it to that form also and implement. That is for you to write. Okay. So now earlier also when we learned how to subtract in the initial classes, we spoke about j. Okay, so in the initial classes I had already mentioned about 2's complement subtraction and 1's complement subtraction. So we do not prefer to do subtraction this way. Why? Because if I go for something like 2's complement subtraction, what is 2's complement subtraction? It is actually taking 1's complement of the number and then adding. It's like adding the numbers, right? Then I add a 1 to that. So I have a number a, a3, a2, a1, a0, and I have a number b3, b2, b1, b0. I take the ones complement, which means b3 not, b2 not, b1 not, b0 not, and then I add it over here. I add a 1 also, right? If I do this, this is one's complement. This what I got is one's complement. Two's complement addition or subtraction means that I take the one's complement of the number, then I add a 1, then I get two's complement. So this step will generate two's complement, and then I add it with my first number. So, so here I have converted the process of subtraction to addition. That means I already have an adder unit, right? I have an adder unit which I can use for subtraction also. So I'm eliminating the need to have an additional hardware unit for subtraction, standalone subtraction. So I can have a unit which is an adder, which depending on the need, whether I have to add or subtract, I can convert it to do the process. All right. So if it is for addition means I don't have to complement by numbers, I have to add them as it is, right? I will, if it is normal addition means I will add A3, A2, A1, A0 plus B3, B2, B1, B0. So I need to have a control there, which tells me should I do subtraction or should I do addition? Okay. So with that, I will be able to use the same module for performing both addition and subtraction. So let's see how we can do that. Now, before I tell you the two's complement adder, I also want to tell you one's complement adder also. Okay, one's complement. See, one's complement adder will do what? If I have number 1001 and I want to subtract 0111. Okay, what will I do? I will write 1001 and then I will add it with 1000. This is the one's complement of the number. So when I add it, I get 100 and a 1 is generated as carry. In one's complement addition, if you remember, I do not know. Otherwise, this carry which is generated needs to be added back to the LSB. So I need to add that. Okay, the end around carry which is generated. If I am doing one's complement subtraction, that means I have my second number which is 0111. I take the ones complement of that number which converts it to 1000, and then I add the two numbers. When I add the two numbers, if a carry is generated, I need to add it to the LSB. That is the rule. Okay. So now I have to do, that means I cannot just take one's complement and add. I have to, after that, I have to add one more thing, right? So, so this is the process of addition, subtraction using one's complement. Okay, this will give me my result. So this is going to be 0, 1, 0, 0. This will be the result of this one's complement subtraction. But I have to carry out this process. So in hardware, this is my adder. And now I need to take 1's complement or not. So I have a C in also, my initial carry in. Okay, that I set to 0. Now each of my bits B0, okay, I have the sum bits generated. Okay, sum bits will be generated S3 to S0. So now if P is equal to 1, that means I'm supposed to perform subtraction. Okay, P equal to 1 means subtraction. And if P is equal to 0, it is addition because I'm using the same unit. Yes or no? I'm using the same 4-bit adder. So if P is equal to 0, let's see. If P is equal to 0, B3 will come as it is, right? Because there is no complementing happening. The XOR gate, if this is equal to 0 means each of the inputs are 0 means B3 will come. This will be B3, this will be B2, this will be B0 and so on. So I get the same inputs. Now I add them. I get the sum. Right. So I am getting the addition output. Now if P is equal to 1, what happens? P is equal to 1 means I can, this becomes, I will complement it, right? When the moment P becomes 1, if P is 1 means this is going to be all of them. This becomes 1. So this becomes B3 bar, B2 bar, B1 bar, and B0 bar. Okay. So I got the complement. Now I am adding A3, A2, A1, and A0 with the complement. Okay, that has happened. Now I said I have one more condition in 1's complement. That is, if I have a carry out, I need to add it back now. Okay. So what I do, I can actually have one more, that is only for the LSB. Okay. One ways I can have a full adder again, or 4-bit adder again. Okay, 4-bit adder. And my S3 to S2 becomes, I will give there S3, S2, S1, S0. And this I give, this carry out should be given to my LSB, right? Yes or no? Addition, where is this carry? Whatever carry was generated was being added to my LSB. So if this is the initial sum S3, S2, S1, S0, and this is your C out, now I need to add this C out to my S0. Okay. And that will give me my final result. Yes or no? Okay. So that means this has to come to my whatever set of this thing. I call it B0. Okay. Then B1, B2, and B3. All of them, what should I make B1, B2, and B3? 0. Okay, I make all of them 0. Because there is nothing to be added there. I only have to add this carry out which is coming to my B0. So then I will get the actual sum and carry out. Okay, so this will be my final sum. Okay. Now here I have one more adder to add that 1. Okay. Now instead of that, that makes again just to add a 1, I have one more adder unit. Can I do away with that adder? Something else can I change somewhere so that I can do away with that adder? This is not, this is just how to do it. Okay. So I have a mux. Suppose if I have a mux. Okay. I have a mux. You remember mux? Mux is multiplexer. I can give two inputs, I get one output. Okay. So I fix one input to 0. Hmm? And the other input to C out. C out. Because my C out, if the C out is 1, I need to add, right? So I am having a multiplexer, 2 to 1 multiplexer. One of the input is fixed to 0, and then the other input is the C out. So what I do is, this is going to be fed to my C in. Okay. So initially I have a control, I have a select signal. Usually I have a select pin. Okay. So this becomes a manually controlled circuit. That is, I have a select pin and I set the select pin. If select is 0, if this is A and B, I'm saying my two inputs are A and B. If select is 0, my input A is selected. That is the rule. Okay. If select value is 0, if I set the select to 0, input A is selected. So initially, what do I want? Initially, I want to add the numbers. I do not know my carry out. Initially, I'm trying to add the numbers. I am complementing the numbers and I'm adding them. Only after adding, I will know if there is a carry out which is 1 or not, right? So initially, I just have to add the numbers without bothering about carry out. So what I do is I connect this to the output. So now this is my Y is the output. So Y is going to be 0. So that is the same as my carry in the first circuit that I drew. It will be the same way. Okay. After some time, that is when I observe my carry out and I see that carry out some value is coming out from my circuit. Then what I do is I manually shift the select to 1. Okay. Select is one input. Okay. It can either be 0 or 1. Which now this I have to do separately. I am doing it manually from outside. Okay. So I have given that control. I have a control through the select pin. So when I set it to 1, what happens? The next input B is selected. And B is actually, I am going to draw. Okay. It's kind of a feedback that I give. You don't have to draw this. I'm just telling you to understand. Okay. We can implement it this way also. In fact, one's complement subtractor is not used. We use two's complement subtractor everywhere. Okay. So if it is one's complement, how to do it is what I'm saying. So one was using 4-bit adder and followed by one more 4-bit adder. Now in order to eliminate the second 4-bit adder, I can introduce a smaller unit called a mux multiplexer, and there I have two inputs and one output, and which output will I get depends on my select value. So I am setting my select value. If I set the select value to 0, input A is chosen and input A is fixed at 0. Okay, it is tied to 0 value. So if input A is 0 and that output of the circuit I tie back to C in. So C in has to be 0 in the normal cases, same way it is 0, and it starts adding the numbers, the complement of one number plus the original A3 to A0. Once that is done and I get some value at my C out, after a specific time, I change the value of my select input to 1. When I make it 1, the other output, C, which is B, will be selected. So B is a feedback from your C out. C out is connected to the second input of the multiplexer. So then whatever is the value of your C out, accordingly, addition, this is the C in, this becomes a C in, and that gets, actually where is C in added? To the least significant bit. Now whatever is your initial C in is added to the least significant bit in addition. A3, A2, A1, A0, B3, B2, B1, B0. I'm adding, there is a C in coming for this one. So this is added here. And this is exactly what I want. If the C out is going to go back to C in, it will be added to my LSB only. This is my LSB. Right? Any doubt, you think over it, and then if you have any doubts, you ask me later. Yeah, sure. Okay. So now let's look at two's complementer. Oh, time is up. Why the bell is not ringing? I think they ring according to the exam timings, I think. Okay.